This is another 2D support reaction problem. Here we have bar AC, that yellow one, supported at point B by a hinge, and at point C by a link, a weightless link that then connects at D to the wall. And we also have a distributed load that starts at constant at 500 newtons per meters, and then linearly increases to 1300 newtons per meters. And we're now asked to draw a free body diagram replacing distributed force by one or more concentrated forces. Then we're supposed to find the force in link CD and then find the support reactions at B. Alright, so maybe we'll get started by figuring out what our concentrated forces are. So I would suggest we do like we've done before, a rectangle and a triangle. So let's do the concentrated force of the rectangle. That would be 500 Newton per meter times 18 meters, 9 plus minus 9. That gives me 9,000 Newton, so 9 kilonewton. And where is it gonna act? So we can say X bar 1 would be right at the middle here. So that would be 9 meters. And let's make sure that we know exactly where. From point A. Alright, that would be our first one. Then our concentrated force for the triangle would be 1/2 times the difference between these two is 800. So 800 Newton per meter, and then 9 meters. And that gives us 400 times 9, so it'd be 3,600, so 3.6 kilonewton. That looks a little strange. Let's clean that up a little bit. Kilonewton. All right. And then the location is going to be 2/3 from this point. You know what? Let's change our description here. Let's say, because both of them kind of fit better to point B than to point A. So let's say 0, and then here we'll say at point B. At point B. And then for X bar 2, right, so it'd be 2/3 from point B. So that would be 2/3 times 9. 2/3 times 9 is, of course, 6. And then here, 6 meters to right of point B. All right, so now we know where they are. In other cases, we've combined them into one, but in this case, we'll see it's easier if we just keep them as two separate forces, so we'll not worry about them here. So let's draw a free body diagram. We'll have our bar right here. Then we will have a support reaction for this weightless bar, right? So the force has to be in the same direction at this bar. So we can say that would be going like this, and we will call that TCD. And we know that TCD is at a slope where this is 4, this is 3, and this is 5 then, right, if we have the other two. All right, what else do we have? We have our support of that hinge. So that will be a BY and a BX. BY and Bx. And then we have our two concentrated forces. One was here. That'd be R1 equal to 9 kilonewton. And then we have another one acting somewhere here. That was R2 3.6 kilonewton, and we knew that this distance was 6 meters. All right. With that, I think we are done. Oh, let's do a coordinate system. But let's leave that in black as usual. Coordinate system X and Y. Let's put our point names in here again. So this was point B. That was point C. And I think with that we have all that we need. So that was our free body diagram, and now we're supposed to find the force in link CD. So B, trying to find the force along here. Now the way that we're going to do that, of course, if we do sum of forces in X or in Y, then we'll have two unknowns, right? We'll have the component of TCD, and we'll have either BX or BY. So let's do a moment around B, because then both BX and BY are going to go away. Equal to 0 is equal to, now I think it's going to be easier to just take this and put it into its two components. So that'd be TC dx, TC dy. All right, so if we do a moment around B, that would be right here, then BX and BY act at the point, as does R1, so neither of those have any moment. Then R2 is turning clockwise, so R2 is going to be negative. R2 times 6 meters, that was that distance that we calculated. Then TC dx is going to go through B because it's along the bar. So that means only TC dy is going to make a difference, and that is turning counterclockwise. So plus TC dy, and it is 9 meters times 9 meters. All right, we're trying to find TCD, not TCDY, so we can say that is minus R2 times 6 meters plus TCDY would be TCD times the sine of our slope, so times the number that's in the up-facing one, so 3/5 times 9 meters. Alrighty, then we can solve for TCD. TCD is then equal to, this was negative, so we can flip it. R2 times 6 meters divided by 3/5 times 9 meters. R2 we calculate up there is 3.6 Newton. So if we plug that in, then we get 4.0 kilonewton, not 40, 4.0. That would be our TCD. That's what we're looking for in B. And then for C, we just need to find the rest of the support reactions. So C, we'll do the rest. Let's do another moment. Let's do the moment around C, so we don't have to worry about what TCD is. Sum of moments around C is equal to 0. Well, what do we get? We get BY, which we're looking for. That is going clockwise, so minus BY times that whole bar was, or that half of the bar was 9 meters. BX is the line of action is gonna go through C, so we don't have to worry about that. R1 is turning counterclockwise times 9 meters. And then R2 is also going counterclockwise, and that was 3 meters. So that means we can get By. By is negative, so all the other signs stay the same. So it'll be R1 times 9 meters plus R2 times 3 meters divided by 9 meters. Now we know R1 and R2 we've calculated before, so that means we can just plug those values in and we'll get 10.2 kilonewton. That would be our By, and then we can get Bx just by doing sum of forces in the x direction. Sum of forces in the x is equal to 0, is equal to, let's see, Bx we have going to the right. The resultant forces have nothing, so we just have CDx. Also going to the right, TCDx. So that'd be Bx plus TCD. Now we're looking at the horizontal part, so it'd be 4 divided by 5, which means we can solve this for Bx, so that would be minus 4/5 times TCD, and that gives me a value of minus 3.2 kilonewton for Bx. Makes sense that Bx would be pointing in the other direction because we're pulling on our weightless link here, so that works out for us. Now, with that, I guess we are done. Yeah, that was everything that we were asked for. Find the support reaction in CD and in point B.